Hello, this is Professor Doug. We are on to Chapter 12 in Hibbler's Mechanics of Materials. And this chapter gets heavy into integration in solving problems of deflection of beams and shafts. So we're going to use Excel as usual to solve several problems, and we're also going to do some approximation using algebraic techniques to approximate the differential equations. So let's get started with an example of a deflection of a beam using Simpson's rule for integration in Excel. We've seen this before in prior chapters we've worked in. And this beam is, if we look at this here on the right, you can see we have a cantilevered beam, right? So we want to know what the deflection is at the tip. That's y, as you see it here under the load, all right? So we have some boundary conditions. We know that the boundary condition at the wall is a length 0, and the boundary condition under the load is the length L. Here it's 144 inches, and the load here is going to be a point load of 1440 pounds, okay? So the length here is 144. We're going to convert that from feet to inches. The load is, this is 10 pounds per inch, all right? So that's a distributed load. And then we also have a point load. So we know that if we do some math, we can put the distributed load converted to a point load at 6 feet from the wall on the right side, right? And then for this particular beam, we have a given quantity of EI. So that's the elastic modulus times the moment of inertia. And that is given in pound inches squared as this value right here. So the first thing we're going to do is set up a column of length from 0 to L, right? And so I'm going to go in 6-inch increments here. And then the second is to create a moment column. And the moment is just the load, right, times the distance. Okay, so the distance across the beam is L, and the load here we're multiplying everything by, in this case, it's 1/2 of the load because it's a distributed load, right? And we're also multiplying by B6, which is the point load here. So our moment diagram looks like this, right? And if we fit a curve to that function, it's y equals minus 5x squared. Okay, so then we want to do Simpson's rule. Well, we have to integrate twice, as you can see here, in order to find the deflection y. So first, if we look down here in the lower right, EI times y double prime is the moment, all right? So that function then is 5x squared, which we've already shown you. This is basically by plotting x versus mx, right? And we're just going to insert recommended charts here, and you can see that's what it looks like. So we've already plotted it, right? And we have negative because the beam's bending downward. All right, so then if we integrate that function, we get minus 5 thirds x to the third minus a constant. So we want to find C1. We want to find out what that solution to that constant is. And then if we integrate again, EIY, right? If we integrate y double, EI is constant, so we're integrating y double prime once to get the integral of the moment function. And then if we're integrating it a second time, we're getting EIY. We want y from this. If EI is a constant, we can parse out y, and that's the deflection at the tip, okay, which is what we want, right? So we want these constants, right? How do you get these constants? These are the equations. We've just integrated by hand here, simple power rule integration, right? So we want the constants, and then we want the solutions to these two equations, EIY prime and EIY. All right, so what we're using is Simpson's rule. We've done this before. We need to know what the interval is here. The interval is 6 inches between each successive length. So I've set that up as an interval column, an interval cell. And Simpson's rule, remember from before, you take the interval, divide by 3, and the interval has to be fixed. The interval has to be fixed at each time, so it's always going to be 6, right? And then we're multiplying it by the first term, which should be 0 here in our equation, times plus 4 times the second term, and plus the third term. So you can just see that here. And we're just going to copy that to every other cell. all the way down to the end of the length L at 144. And then we're going to sum all that. And when we sum this column, we get constant 1. There it is. So if we plug constant 1 into this EIY prime equation, as you can see it here, minus 5/3 x cubed plus C1, we're going to get the solution to that equation. Likewise, we want y prime. Y prime, we know, is the integral of the moment. So it's minus 5/3 x cubed plus C1. So you can see that here, right? And here it is. And so we've got a y prime for each value of x. So let's take a look at that, right? And what we're doing is taking 5/3 times, in this case, it's h4. So h4 is going to be the x value. And then we're adding j30, which was j30 in this case was our constant, right? So we want to calculate a column of y primes. And the constant C1 was solved by Simpson's integration, Simpson's quadrature. We just summed all those Simpson's rule values to get C1. And then we are doing Simpson's again for the y prime column. Same type of formula structure, interval, divide by 3 times the first term, plus 4 times the second term, plus the third term, and then we're copying that to every other cell all the way down to the bottom, and we're summing that column. We just take a summation of this column. That's our constant 2. So our constant 2 appears down here when we integrate twice. So the solution to that equation, EY prime, is shown here. So we have a solution to EY prime and EI prime and EIY. Those are the solutions, right? So then y then becomes, we just plug that into the last solution and divide by EI, all right, to get y isolated. And here they are. So we want to take the value here, and I think what we can probably do is take the maximum value, right, at max of this entire column. And there it is. That's our solution, right? So I just highlighted it in yellow. So that's our deflection. If you take the entire equation and just divide by EI, you'll get the value. And we know our constants now, C1 and C2 by Simpson's. Plugging them in, we get EIY prime and EIY. These are the solutions to those equations. If we just divide them by the EI value, which was given, we'll get our deflection at the tip. And here you can see it's done by hand in a rendered notes format. Okay, what if we don't use calculus? So what can we do? Well, we can use a method which is described in Strength of Materials by Den Hertog, classic text, and that's called the Myosotis method. And what it does is actually, you're looking at these 6 equations, right, of different beam loading, cantilevered beam loading equations. And these are for angle and deflection. We want deflection, okay? And so we're going to be looking at the second one. And what you're really doing is looking at sort of 2 cantilevered beams in sort of an image, a reverse image facing each other, and you're getting deflection of both at the tip and then summing them together. All right, and so you can see the graphic here for the Myosotis method as posited by Hertog, Den Hertog, is that you have a movable load P along the length L. And then for everything to the left of P is going to be called A, lowercase a, and everything to the right of B is going to be called lowercase b. If P is in the middle, then A is equal to B. If P is off to the right support, then A is equal to the length, and there is no B, 0. If P is on the left side, then it's all B and no A. So you can see X is a function of A and B. X is the length here, right? So A plus B equals X. All right, so then you've got your curve underneath the load as it moves. That's lambda. And if it's in the center, then the maximum of that's going to be right under the load, right? But in our case, in this example from Hibbler, example 1226, I believe, right? The load is here. And so the load is about 2/3. It's 12 feet long. And so you've got the load 2/3 of the distance from A to B, 8 feet. Okay, it's a 3 by 6 beam, so you can see that cutaway on the right. The elastic modulus is given. It's made of wood. What's the maximum deflection? Okay, so we can use the Myosotis method here algebraically if we don't want to do integration like we showed in the last example. So the load is 600, the length is 12 feet. Let's convert it to inches. From A to the load is 8 feet, 96 inches. From the load to B is 4 feet, 48 inches. The base is 3, the height is 6. So the area is 3 times 6 or 18. And the area moment of inertia is 1/12 of the base times the height cubed. There it is, 54. Elastic modulus was given. We're going to convert it to PSI, okay, for this type of wood. And I don't know the type of wood. So we're going to construct a couple of tables. The first table is just really a reiteration of what you see here. L, B, and H, right? Length, base, height. The area moment of inertia. These were all calculated previously. Elastic modulus. Here they are. Load 600. So we want to find our maximum delta, our lambda, all right, based on where this load is. So we set up from Myosotis, we set up based on these equations in red, right? X, as you see here in the diagram, is the square root of A times A plus 2B over 3. And y, which equals the lambda here that we want, right, is p minus pbl times x cubed over 3I. And that comes from the second Myosotis equation here on the right next to this equation 20. All right, so we can set up our table of A from 0 to 144. Now B is going to be, and I did it in increments of 6 inches, okay? Because this is a 12-foot beam. Now, you could pick anything you want, but I thought 6 was good enough to give us a nice, robust analysis. And we're not doing Simpson's rule here. We're just algebraically calculating the answer, right? So A, whatever A is, B is L minus A. So if A is 0, B is 144 minus 0. If A is 144, then B is 144 minus 144, or 0. So these are, there's a midpoint at 72 inches where they're equal to each other, where the P load would be in the dead center, right? Half of, that'd be 6 feet. Okay. So I have that here on the right just for reference, right? So X and Y are really the calculations. So X is square root of A, this A, plus 2 times this B over 3. And there it is, right? And then Y then is the deflection. So that's minus PB, the load P, which is a constant. B using this B, not the base of the board. I called that of the prismatic beam. I call that capital B in this table, right? It's minus P times, in this case, minus P times a B, the lowercase b, divided by the length, right? The length as a constant, okay? Is that right? Let's check that. Yes, times x, this value x, whatever we calculated, cubed, divided by 3EI. 3EI is going to be a constant. And we are dividing by L in this case. We're multiplying by L in this case, multiplying by the length. So then we know that unloaded, we're not going to get any deflection, right? So here's our deflection. Y is our deflection. We could plot this if we'd like. We could plot X versus Y. And actually, we want to plot A versus Y in this case, right? Because A is the length. And if we did that, let's see if I can get that to happen, right? If I can do that. And we would insert a recommended chart there, and you can see the deflected beam, right? Here it is. But this assumes that, P is at the center, but it's not. So what do we have to do to solve the problem? We just simply look at where is P. Well, P is at 8 feet from the left, and so 8 feet from the left would be here, so the answer is minus 0.396. All right, so that's your maximum deflection, right? And these are all the deflections for different locations. And it just so happens that our load is located here in yellow and not at the center, okay? So that's our maximum deflection under the load using the Myosotis method. Okay, last problem by energy methods. Very interesting here. So this is on a assumption that if a load F is applied to a member, here's a stepped beam. And as a result of the member deformed at distance y, so there's going to be a deflection in y upward at the tip. The work done by that load if the relation between the load and deformation is linear, which it is given as this equation. U equals 1/2 of the force applied times the deflection, y. And so we want to look at the bending moment, the elastic modulus, the area moment of inertia. So we know that our strain energy is m squared L over 2EI, right? All factors are constant with x. So if we integrate this, we're going to get the integral of m squared over 2EI dx from 0 to L will give us our strain energy. Once we solve this equation, we integrate this equation, we can plug U back in here and multiply it by 2 and then divide by F, and we get Y, our deflection. So we did this one by Simpson's rule. So here we've got our elastic modulus is given. You can see in the small print 210 GPa. So I put it in pascals. The force is 1,000 newtons upward, so it's a stepped, remember, and it has a length of 1.9 meters. So that's a little bit problematic because it's hard to divide that evenly for Simpson's rule. So we'll show you that ours is pretty much a close approximation. So there's a H1 segment, I'll call it H1, and then an H2 segment. They're both L over 2.95 meters, right? The height, each of them has a width, these segments, of 0.02 meters. So the widths are constant, but the heights differ. So the height of H1 is greater, twice the height of H2. Hopefully that's clear. And so we want to know right away, what's our integration constant? What is 1 over, see, you can see here in the integration, 2EI are constants. So we're going to pull that out of the integration. What's 1 over 2EI? Well, EI you have to calculate, right? So E, and then you have to figure out I based on 1/12 of the base times the height cubed. So there's your EIs. You've seen these before. So these are constants. So I'm pulling these out, right? EI for H1 and EI for H2. And the units are Newton meter squared, okay, for those EIs. So our integration constant is just 1 over these, right? So I'm just taking a 1 divided by 2 times that. Sorry, it's 1/2, right? 1 over 2 times the EI constant. So there they are. All right, so let's keep those in constant. We want to calculate the elastic strain, so we need Simpson's rule, right? But here's our length. I broke this up into 2 sections. The L2 H1 section in this part of the table, and then the L2 H2 section in the second part of the table. And for this, I have lengths from 0 to 0.95. And I just, for fun, I said, what percentage of the length is that? So we get down to 50%, right? And then we have our force times our distance, right, x. So I'm just taking the 1,000, which was the force applied F at the tip, right? And I'm multiplying that by the length. That's it, all right, upwards, so keeping it positive. So then we have to square the moment for the integration. So I'm just simply squaring whatever the quantity in column I here is. I'm squaring it, right? So there it is. Okay, so there's our bending moment. And then you can see it sort of repeats and picks itself up for the next section, the H2 section on the right, L over 2. Okay, so Simpson's rule, again, here we are. What's the interval here? Well, the interval I use is 0.05, okay? However, Simpson's rule needs an even number of sub-intervals per segment. And with this type of a geometry, there's no way to make the panels land on both x 0 to 0.95 and x 0.95 to 1.9, the total length, cleanly with that step size. So what are we going to do? Well, this is the issue. This is in red here, right? That's the caveat, the warning. So I picked the interval of 0.05 for now, right? So Simpson's rule, you can see we've done it before. We take the interval, divide by 3. That's going to always be a constant, times the first term here, which is the 0 term in the moment squared. That's what we're integrating, right? And 4 times the second term plus the third term. There it is. So there's my Simpson's quadrature calculation. I'm going to copy it down to every other cell. We got a problem. We didn't make it to 0.95. So it's going to underestimate slightly. So this is a summation of everything that we see here. In the last one, I've just created this. I got a blank cell. So this was really not a clean approximation, but it's close. And then I did the same thing for the second half of the step being the smaller, less tall member, H2, same distance, L over 2, but now it's 0.95 to 1.9, right? So that one, same thing with Simpson's rule. I'm ending up with, a shortfall. Okay, so what did I do about that? Well, my strain energy then is just the, if you think about it, right? It's the integral of this, which is Simpson's rule, from 0 to L. So here it's 0 to L over 2, and then L over 2 to L. And then I'm dividing it by 2I, and that'll give me my U, my strain energy here, right? My potential energy due to strain, right? So that's it. I'm just dividing it by the integration constant, right? Or multiplying it by 1 times 1 over 2 EI. That's all I'm doing, right? You can see that here. Okay. So the elastic strain due to energy in Newton meters, that's joules, that's energy, are these numbers. And I'm just going to sum them, and divide by if you look over here, I want 2 times U divided by F, right? So that's 2 times the summation of the U, elastic strain, divided by the force. It's going to give me Y, my deflection. There it is, 0.195. Well, I've done this integration by hand and also computationally in MATLAB, and that's really not the answer. The answer is 0.191. So we have this sort of shortfall due to Simpson's rule not falling exactly in an even number of subintervals. So one of the things we could do if we knew the answer a priori was to say, maybe we should make the interval, smaller, right? So how could we do that? If I already know the answer, which I do in this case, I would be probably using what-if analysis, goal-seek, bring that over here, and I would set this up to the answer, 0.191, and you could change the interval to do that, right, and see what the new interval will be. Turns out it's like 0.049, so it's really close, right, and that would give me the exact answer there, but we're not going to do that. We're going to leave it as an approximation. It's pretty close to the actual answer of 0.191 or 19.1 centimeters with 1,000 Newton load. So that's using energy methods, which is really quite interesting, I think, for this method. And we've seen 3 ways to calculate deflection of beams, and some algebraically, some using calculus, Simpson's rule, and hopefully this has been helpful for this chapter because it's quite involved.